All right, recording started. Sharing the screen. All right, now I'm sharing the screen. Last time we started we stopped at the single phase, I think, transformer. So here's the transformer, and I believe we stopped here at the single phase three winding transformer. So this is called single phase three windings. Three windings means we have um, first winding here, and second winding here, third winding here. So it's called three windings transformer. And it is used a lot for example, like United States, Saudi Arabia, but this is not common in Jordan. This is not common in Jordan, but used a lot in United States or Saudi Arabia. Okay, and as an example, or how it looks like, this is the picture, or there's another picture for that, or another drawing like this. So the thing here, we have the voltage at 7.2 kilovolts, and the other thing, or the other side, plus minus 120 volts. Here is plus minus 120 volts. Then here, this is phase A and B. This is A, B, and neutral. Or let me call them as lowercase a, B, and neutral. Then what's the purpose of using this in USA or like on KSA, either of those? So they have dual voltages in distribution. There is voltage called like there is a voltage 120 volts, and there is another voltage 240 volts. Both of them, again, they are used. Um, then we have dual voltages. How can we get 120 volts? By connecting A to neutral. How can we get another 120 volts, B to neutral? But if we need to get 240 volts, then we will connect A and B. Then we can obtain 240 volts when it is needed. Then here's like the connection. We have hots, and neutral. So when we put hots, you can say like this is A, this is B, this is neutral. Then if you make it from here to here, it will be 240, while from here to here 120, from here to here 120. Okay, now there's a question like in my mind, why there is two voltages, 120, 240? Why don't we stop at 120 and say, let's stop with 120 and that's it? The main reason for that, which is related to the applicants or the like the load. Some loads, some loads consuming or consumes a lot, consume a lot of power or large amount of power. I would say, let me say, large power. And as we know, the power equals V times I conjugates. If we put V 120, then we can say S directly proportional to I. Then it will be directly proportional to wire size. So in some applicants, if we have 120 volts, you need to have a very big wire size. However, if we make it 240 with the same S, you, you might need lower wire size because lower I, lower size. So when we make it lower size, this can be applicable for large loads. So those large loads, as an example, air condition. If you have a central air condition, also the air dryer, Those are as an examples of loads that are consuming a large amount of power. Also, you can put your EV charger as well. So in those devices, 120 volts is not sufficient enough to supply power for this type of instrument. So we need to have a 240 volts. That's why in like in USA or KSA, you will see dual voltages, and you will see like each plug separated with, separated plugs with each one. So 240 is used in central air condition, used in air dryer and some other instruments, while the 120 volts will be used for the other applicants. I'm talking about residential. And the other thing, or the other question, why there is 120 volts? Why don't we stop at 240 and say, let's make it the standards? The answer is we already have this in Jordan, like 230 volts is the standard. There is no need to reduce it to 120 or 110. While in the other part of the world, they prefer to use 120 or 110 for safer level to reduce. When you are reducing the voltage level, then you are making it more safer, so there will be less fire hazards or less electrocuted hazard than for safety using lower values of voltages. Okay, so this is again, this is called service, or I would say like distribution transformer, single phase distribution transformer. Single phase distribution transformer. But again, this is not used in Jordan, but this is used in other parts of the world. Okay, here is how about using the first one, single phase distribution transformer, but I would say like 3 windings. Single phase, 3 windings. 3W means 3 windings. While these two transformers, those are called single phase 2 winding transformer. Why 2 winding transformer? We have primary winding and secondary winding. Just that's it. We don't have 3 windings. So in these parts, you will see they are connected to convert, for example, 7.2 kilovolts to 120 volts directly. There is no 240 volts. That's the thing about it. And there are 2 types. The first type, by grounding the neutral. The other type, neutral is not grounded. Here is also the other part of the connection by using 120 volts. There is by grounding a neutral and by not grounding the neutral. So sometimes you can connect it to phase A and B or phase A to neutral. It depends on like the situation, or depends on the connection. Um, the other one here, converting 7.2 kilovolts to 240 directly volts, not 220 or not 120, it's 240. So this is also used in case if we need to have a load 240 volts directly. Again, those type of transformers are not used in Jordan, just like you might find them weird, but yes, we already have them, but in outside of Jordan, in other part of the world. Parallel operation of single phase transformer for additional capacity. The sometimes when you need to connect extra loads, maybe the transformer ratings will be insufficient. So how to solve it? By replacing that transformer by another one. Or in case if you don't want to replace the transformer, you can install another transformer. So you can make it parallel. We already talked about the paralleling transformers in the last lecture, but here we will talk about single phase paralleling, which is different than the 3-phase paralleling. It's very same, which is same voltage, same percentage impedance, frequency must be identical, tap changer identical, combination must be identical. But the thing, there is no rotation or there is no phase sequence. That's the thing that you need to keep in mind. Then again, here is like how we do the paralleling the transformers. Same polarity, if it is additive or subtractive, there must be the same polarity. Tap changers must be the same. Voltage ratings must be identical. Frequencies identical. the percentage impedance must be between 92 and half to 107 and a half of each other. So we need to make sure what we prefer is to be identical percentage impedance, but if not, they can be between 92 to 107% identical. So we don't want to have the loading on one transformer more than the others, then which will create some problems. Three-phase transformer, sometimes we can create a three-phase transformer from a single phase. So we can say, in order to get a three-phase transformer, we can have the same one that we already discussed before, or we can say it is a 3 times single phase transformer. Sometimes we can say a shortcut for the transformer, XMER. This means transformer. So 3-phase transformer equals 3 times XMER, single phase. Okay. Here is how it looks like. This is delta connection. So in order to make a 3-phase transformer from a 3 single-phase transformer, by making the delta connection, and as we know, the delta here, the inputs or the output of the first one will go as input of second one. The output of the first one goes as input of the second one. The output of the first one goes as an input of the third one. Then they all could be connected to phase A, B, and C. This is delta. And delta from the other side, it's also like this. The first one go to the next one. Then all of them, they are connected to phase A, B, and C. Okay, the other one, it's the same, but with displacement angle 0 degrees, while the other one with displacement angle 180 degrees. So in the displacement angle, I think it's not clear in this picture. How can we get the angle 180 degrees? So I would say, don't worry about the displacement angle. What we need to worry about is just like delta to delta or delta to y or y to delta or y to y. That's what we need to worry about. While the displacement angle here, it's not clear justified, then maybe in the future I will fix it, but not here because here it is not, I mean, the lecture notes, it's not clear mentioned how to make the displacement angle. But here is another one. To get a three-phase transformer, then we have a neutral grounded. We created a neutral for the delta, which is something new to us. Then by making the connection in between A to B, creates in the middle wire to make connected to the neutral and to the ground. Then here is the middle connection, then we make it with the ground. Then with this connection, we can obtain 3 voltages. There is 120, 120, and 208. 208 means this is line to line, 208. To make it line to neutral, which is 120, 120. That's something can be new to us. So in order to make, here is we created a neutral. So we created phase B with a neutral, phase A with a neutral. That's the thing. But if we need to make it with phase C, it will be 208s. So you need just to think about this connection as we have 3 voltages like 208s, 120, 120, and the other side 208s, not 120. Here is the other one, but by making it between phase A to B, making displacement. So again, don't worry about the displacement here. The displacement was 120, 180. Here is the displacement 0. So it's almost the same. Nothing changed, the same as the previous one. But this displacement is, instead of being 180, it will be 120. Again, as I said, like don't worry about the displacement. Let's keep it as is. Here is y to y. In order to make it y to y, as we know the y, the live are connected like this. Those are the lives to phases A, B, C, while the neutrals, they will be connected together here, then toward the neutral. Then the same thing in this secondary side. Then here are the neutrals. You see, these are the neutrals, while the lives, This is the live phase C, live phase B, live phase A. So you need to know the connection by looking at the picture. Then you need to know that this connection, is it Y to Y? Yes, this is not Y to delta, not delta to Y, not delta to delta. And there is nothing like Y with delta neutral. That's the possibilities. We can say like any of these four possibilities. And also, when you look at delta, there's another possibility to be the normal delta or delta with the neutral by connecting a virtual neutral. Here is another one. This is y to delta. How can we know it is y? Look at the primary side. This is the primary side. This is y. And look at the negative side or the returning side. This is connected to the neutral. Therefore, it is definitely y. Then when we need to look at the secondary, um, the secondary is connected as delta because here the entering or the x1 connected to the positive here to connect to the negative side, then the positive here connected to the negative side, and the positive here connected to the negative side. Then the phases, they will be connected. This phase A, B, C, and we created the virtual neutral or created the neutral in the middle of between A and B to create the neutral. Therefore, we have 120, 120, 208, and of course we can create the 240 from connecting these to 120, 240 volts. Therefore, we can say it is this connection is Y to delta with delta neutral. This is a special interconnection by creating a neutral to delta, while as we know delta doesn't have a neutral, but here we created it. This is connection. Let's look at it. In this connection, we will see that the negative part connected to the neutral. Then we have this is a live, and live. Therefore, this is Y connection again. And when you look at the secondary side, in the secondary side, you will see that which is connected as delta. Then those are the phases for each one. So this is connected with delta. Therefore, it is delta connected, Y to delta. And again, as I said about the displacements, don't worry about the displacement angle. We will talk about it later on. This is also another Y to delta with a neutralize. There is a neutral for delta. And this part's delta to Y. So delta, again, look at each one. Then you see it is delta, while Y, the negative part, all of it connected together. Then while this one, phase A, B, C, and that's it. This is the last one, almost the same, delta and Y. Okay, any question about this chapter? Now we are done with the transformer. Any question? Is this clear?
So these are just the connections, how they're connected, like delta to delta, Y to delta, like what we discussed in chapter, it was in the second chapter, right?
Yeah, the connection, yes. But now here it's more details, like about some details like special case for the delta with the neutral. And again, don't worry about the displacement angle, but that's what you need to know about the connection. So like this, if you have a connection like this, then you need to determine what's the primary, what's the secondary. Then when you browse or try to see, label the phases, you will realize this one is delta. Okay, understood? Now, let's move to the next chapter, which is related to the high voltage cables. Okay, high voltage underground cables. In the previous chapters, when we discuss the transmission line over system planning, this one, all of them, they were related to the overhead transmission line, like this. Let me show you those models, those towers, all of them are related to overhead transmission line. And when we talk about the conductors, we mentioned there is all aluminum alloy conductor or all aluminum steel reinforced, which is zebra and yellow conductors. That's what we discussed before. So all of them, they are related to overhead transmission line. But as I said, we can have underground cables or not underground cables or submarine cables as well. So underground cables, uh, we have a few underground cables in Jordan, but they are very dummy. I mean, they are very important. Studying this is very important. And we have one submarine cable lines between in Jordan, between Aqaba and Taba in Egypt, between Jordan and Egypt, which is submarine cable. I believe it's around 20 kilometers, something like that. I'm not exactly sure about the length, but there are submarine cables there. While the rest, we have several underground cables. They are especially in Amman area to connect between, for example, like university substation to Abdoun, and between Abdoun to word city center, وسط البلد وعبدون and جامع الأردنية. So those interconnection between or the interconnection is not overhead transmission line. There will be underground cables. So we have them as underground cables because the land prices are very expensive. We don't need to, we don't want to spend a lot of money on purchasing lands there to make the underground cables. And in addition to this, in military, when there is a military base, we prefer to put underground cables because sometimes the military can do some trainings. We don't want these trainings to impact the overhead transmission line. Therefore, we put them underground cables in some areas, or sometimes we just remove or just like puts the what I say, like the power lines away from the military substation. But in case if it's, I mean, a must or it's mandatory to the power line to go inside a military substation, we will put it a military like area. We will put it as underground cables. The disadvantage of underground cables is the costs. So here, like again, the introduction. As we know, the electricity is being generated from the generator substation, then going to the customers through the transmission line and sub-transmission line areas. Then the problem when we transmit the large power for long distance, we need to use which is we need to use high voltage. Therefore, we create this creation, the transmission and distribution system. The transmission system will deliver the power from the power substation toward the load centers, whereas like toward close to the loads, the city centers, or close to the large industrial customers, or at the entrance of the cities, while the distribution system will deliver power from the substations toward the various customers. Now, the generation, again, as we said, just overview, we have generation in 6.6 kilovolts, 11 kilovolts, 15 kilovolts, or 3 kilovolts, while the transmission, basically, we have, the standard in the worldwide, we have 132 or 220, 400 kilovolts, 700 kilovolts, 1200 kilovolts. This is very common worldwide, while again in Jordan, 132 kilovolts and 400 kilovolts. Those are very common, the main two. And as we said, like there was in the past 230 kilovolts, but it no longer exists because it was the serial connection between Jordan to Syria. So between Jordan to Syria, that was exist before, but now it's no longer exists. We still have a connection between Jordan to Syria, but it's de-energized, which is 400 kilovolts. It is ready to be electrocuted at any time, whenever needed. Okay, now, as we said, like the primary distribution voltages in Jordan, 33 kilovolt and 11 kilovolt, depending on the requirement of the customers. And the distribution is 400 volts. This is, we already know that in Jordan. Why we said it's 400 volts? 400 volts or 0.4 kilovolts, because when you divide by square root of 3, it will be 230 volts. This is line to neutral, while this value is line to line. Then the overhead system, as I said, and there is underground systems. That's how we do the transmission and distribution.
Just
So
a quick
then,
question. Why
yes.
do we not talk about wireless power transfer? Why do we only talk about physical power transfer?
Okay, that's a good question. We don't have a wireless power transfer in transmission and distribution. We don't have it for as a power transformer or a power delivering a power large value. The power that I mean something like 2.5 megavolt ampere or like 5 megavolt amperes and larger than that. So this we call them power, like power transformer or even distribution transformer. We don't have a wireless power transfer in this. What do we have in wireless power transfer? Which is basically in very small values, below than 1 kilowatts. And we have them in small applicants like wireless power charger for wireless power EV chargers, or wireless power chargers for small, very short distance, which is basically less than 1 meter. We don't have them. We don't need them to in distribution or in transmission. So we cannot make a power transfer from area like from one substation to another substation, and the distance is 40 kilometers. We don't have them. If you go to, if you, when you read in the past, Nikola Tesla tried to do this to transfer the power for long distances, but there was, a lot of safety concerns, and right now we don't know how he built it, and there is no information how. There is no research about doing a wireless power transfer for very big distance. What we have them so far or nowadays is basically related to short distance in centimeters or meters. Like for example, you can make a wireless charger for your cell phone, but your cell phone will be directly attached to the wireless charger. A wireless charger to your Apple Watch or like your watch, a smartwatch, then okay, wireless charger for your electric vehicles, but it will be very short distance. It would be less than 20 centimeters. Even though they can do a wireless operation for the some like TV or on any other devices, but those can be for 1 meter. Maybe like, but in terms of kilometers, there is no way so far. I mean, Nikola Tesla did this before, but we don't know how. And I would say like there is no research nowadays about making wireless power transfer. One of the biggest thing is the safety, because if you need to put a tower and a tower, another tower to make a wireless power transfer between these two, then how about if there are some birds in the middle, or if there are some people in the middle, cars, etc. So there will be safety concerns. So again, nowadays there is no research at all to do a wireless power transfer in long distances. Okay. Then, if anybody interested in reading more about the wireless power transfer, you are very welcome. You can, I can guide you on some references, but I would say it's not part of the distribution transmission system or generation. It's just part of we call it consumer electronics, which is just like in not attaching a wire to charge your cell phone, just put it there, then it will be charged. So as I said, let's continue. There is overhead, um, transmission line, there is underground systems. So the main reason for using underground systems, it will be used most likely in populated area, like towns, cities. So whereas the use overhead transmission line is not practical, where because there is a high cost of land. As I said, in Abdoun, and downtown of Amman, where like it will be very difficult to put overhead transmission line systems. The land is very expensive and it's very crowded area, very dangerous to put overhead transmission line there. There is no space to put overhead transmission line. Then we make it as underground cables. And again, why, or the other question, why don't we make all of the power lines as underground cable? The optimal thing or the optimal scenario is to make everything underground cables. Then it will be, the safety will be very good. But there is a problem about it, which is the cost. It is very costly. I remember one time we made a study about to convert one line from underground, from overhead to be underground, and I believe the cost was 9 million for 20 kilometers. 20 kilometers. We need to make it, replace it from overhead system to be underground system. And it cost us 9 million JDs. 9 million JDs. This is very expensive. So as I say, like, let's use or I mean, in this situation, is it deserve to spend this money on making underground cable? Does it deserve this? If yes, then okay, let's make it underground. If no, this is too much, then okay, let's make it as underground cables. Let's make it overhead transmission line. Here, in the electric, when it's transmitted on underground cables, the cost, overall cost, because we need to have an insulation, and the installation is very high. As the voltage level increases, the cost of insulation increases as well. So therefore, the underground cables is basically restricted in low and medium voltage when we have in distribution, while we have some underground cables in high voltage. But in Jordan, the vast majority of underground cables, underground systems, is associated with low voltage and medium voltage. You can find them in Amman. You go to the downtown areas, downtown of Amman, downtown of Irbid, there is no medium voltage overhead transmission line. There will be underground cables as a medium voltage and and low voltage. However, when we are talking about high voltage, you will see them in Amman, underground cables. In Amman and its suburbs. But when you go outside of Amman, for example, let me talk about Irbid. There is no underground cables in Irbid, except there is one line in when you go close to the city center, it will be, I think, around 2 kilometers as underground cable. So there will be overhead, then it will start directly to be underground cables around 2 kilometers to go to the substation. But not a full line, it's not like the connection between Abdali and Abdoun areas, or between Abdoun to city center, between Abdoun to the university. So you will see, I mean, a very big network in underground cables over in high voltage. But in Irbid, not a lot. In the other cities, not a lot. I mean, we barely see them. We just see them in low voltage and medium voltage. But I would say like most common in medium voltage. The vast majority of underground cables in Jordan is related to the medium voltages, which is, I would say, 11 kilovolts, more than 33 kilovolts. So 11 kilovolts is used a lot. 11 kilovolts is used a lot in underground systems, underground cables. So what's the reason behind that? Which is the cost. When you have a high voltage, you need to use a larger thickness of insulation. A larger thickness of insulation means more money, spending more money, increasing the cost. Therefore, high voltage cables is very costly. Again, as I said earlier, in high voltage, to make it underground, from overhead to underground, it takes 9 million JDs, which is too much. While When we are talking about low voltage, it will be less, way cheaper than that. Okay. Comparison between overhead and underground cables related to the safety.
Can I
Yes.
jump in? Why can we see like sometimes like entire cities that have like underground cables, even though it's very expensive and sometimes it's hard to maintain if there's a problem in the line? Like, what would be the incentive to do that?
So the inside the cities, we'd like to make them underground cables because um, one of the things they are using the ring connection. You know the ring connection, right? The ring connection between the
Yeah.
substation. Yes. So that's one thing. So to make a more power system reliable. The other thing, we will make them as underground cables because inside the cities there will be sometimes like some pollutions, if like for example industrial cities, or sometimes like there is a lot of, I mean, they're afraid about the car accidents, so we don't want the poles fall down, or we don't want when there is some like very large buildings. And the other thing also related to it, which is we need to make sure the view of the city looks nice. We don't want the view of the city, we don't want the power lines ruin those. So that's why inside the cities we put them, we use underground cables, especially I'm talking about the medium voltage. So you will see like the downtown areas. So they say like, okay, let's spend more money. That's fine. And the other thing, which is, as I said, like the land costs a lot of money. So we are using this. I hope this answers your question.
Yeah, thank you.
Okay, you're welcome. Now, let's talk about the comparison between overhead and underground systems. So related to the safety, so again, underground system, we call it UGS. Overhead, we call it OHS. Overhead system, underground system. Related to the safety, underground is way safer than the overhead. So the overhead, it will be, I mean, threaten the people around us because if, for example, there's a car accident or if you're making a construction under the power lines, it will be damaged. So related to the safety, or you will be electrocuted, I'm sorry. So they will related to the safety, of course, underground is safer. Related to the initial costs, underground system is more expensive. And the cost is around 4 to 5 times the overhead system. That's something that you need to worry about. That sometimes the overhead it's cheaper 4 or 5 times than the underground systems. That's something that we need to worry about. The other thing, which is the flexibility. The flexibility of the overhead system is way flexible, more flexible. Why? If you need to make any substation or in like I'm talking about the medium voltage, if you need to make any distribution transformer, you can install it at any pole you want. While if you need to make a step down or distribution transformer in low voltage, you need to look to search. There is a specific areas that you are allowed. You cannot make it anywhere, so it's not flexible. So if you need to make any load expansions, or make any new conductors, in the overheads you can make it, while in underground, um, I mean, you will be limited. You cannot do it everywhere. The other thing, the maintenance, the underground cables or systems is difficult in maintenance, while the overhead system is easy. Why? Assume there is a fault or there is line-to-line faults. When you send the maintenance team will search for the where is will search for the fault. Then they will see it by their eyes. Then they will say, okay, there is a, I mean, the line, one line is disconnected. Then they will fix it easily. While in underground systems, when they need to do the maintenance, the fault can be under the ground. They cannot detect where is it. They need to search for it. They can use a device which is called Migger. We will talk about it later. There is a device called Migger to identify the fault location. Identify the fault location. So, which is not easy. Once they identify the fault location using the Migger, they will send the maintenance team there. The maintenance team, they will, once they identify, they will start digging and look for the wire. Then they will start to fix it. So the maintenance there is costly, difficult, while while the possibility of getting them, I mean, a failure or a fault is low compared with the high voltage. So this is a drawback of the underground systems, which is difficult in maintenance and difficult or very expensive. And the initial cost is also costs a lot. While the advantages, which is the failure rate is low, the safety is good. So the failure rate in underground cables is low. So because the insulation is better, very few chances of power failure, while overhead systems, there is high chance of failure due to lightning strikes, snow, heavy rain, like wind, heavy wind or like large, I mean, the wind as well. So therefore, then we can say the failure rates for UGS is low compared with failure rate of OHS. Here is the chance about the failure rate for each one. When we talk about low voltage levels or like 11 kilovolts to 5 kilovolts, the failure rate is 0.048, while for OHS 0.177, so we can say this is higher. Then between 11 kilovolts to 20 kilovolts, when you see like the failure rate is reduced, or no, it's increased actually, but you will see in overhead is more. Then 33 kilovolts, the failure rate of OHS is also higher. Then 66 kilovolt, the failure rate is higher. Then we can see when you're increasing the voltage, the failure rate decreases in overhead system. And underground system, it is decreases here, while in this part increases. So you can see between 11 to 20 kilovolts, the failure rate increases. What's the reason behind that? I would say the reason because the availability, because the vast majority, of underground systems is 11 kilovolts. Since the majority of is 11 kilovolt, that's why the chance of getting a fault for under 11 kilovolts underground systems for 11 kilovolts. The frequency of accidents, again, the frequency of accidents in underground systems is low compared with overhead systems. The other thing, the voltage drop. In the voltage drop, we can say, when you look at the spacing between the phases, like three phase, we will talk about the phases later, but like the spacing between the conductors, here is the underground cables and it's filled with insulation material. So the space here is low, low, low. Then we can have a capacitance between the conductors. And the capacitance, which is epsilon times A divided by D. D, which is the distance, or I believe it's epsilon D divided by A. Let me double check. Epsilon D divided by A, I believe. So whatever. So the thing that I would say, like, C is directly proportional to the distance. Or no, it's inversely proportional. So I believe it's the other thing. Epsilon A divided by D. So C is inverse proportional to the distance. So when you get shorter distance, C will be high. C will be high. This reflects on in the underground systems, the equivalent circuit for it is a capacitor. In overhead transmission line, the equivalent circuit, resistor, inductor, and there is a capacitors here. While in underground systems, the equivalent circuit, we will talk about it later, but it's like based on a capacitor. So when there is a capacitor, this will, in underground systems, this will make we will talk about it, it's not 100% it's not 100% the equivalent circuits for the underground cables, but we'll talk about it later. But I would say there is a capacitance. So the capacitance will boost the voltage, will work as a power factor improvement, and they will work as increasing the voltage. So they will increase the voltage because they will work to supply reactive power. Once they're increasing the voltage, we can say the voltage drop in underground system is low, very low, while in overhead transmission line there is a voltage drop because there is an inductance there. The appearance, the underground system is better because it's good looking, because there is no wire visible to us, while the overhead transmission line, there is a ground, we can see it. Charging currents, since the fact that the underground system cable is actually a capacitor, they have a high charging currents. So when there is a high startup currents, which will try to absorb a lot of voltages, a lot of electric field inside it, then it will take a lot of energy there. Then if we need to do the maintenance, we need to discharge it. So it will take a lot higher charging currents compared with the um, overhead system. Jointing jointing in the overhead transmission line is easy, while when we do it with overhead in underground cables is difficult and requires extra precaution, because the jointing there, we need to make sure it is neatly done and perfectly done. We don't want to make it bad joint. Bad joint will create a problem and create something we call it hot spots that will be severe and cause damages to the underground cables, especially at the joints. And the vast majority of the faults in the underground cables happening at the joints, by the way. So we need to make sure the joints must be done by expertise, by expertise. So we need to make sure they can do it in a perfect way. And there is no, and they are doing the joint, we need to make sure there is no, I would say, no problems, no, no environmental impacts. So it must be, again, very neat. So damages due to lightning and thunderstorms. So underground systems is free from interruptions of services on account of thunders. There is no thunderstorms, there is no lightnings, strikes, there is no winds there, so which make it a good. Fault location and outage duration. It's very rare to have faults in underground systems. But in case if there is a fault, it's very difficult to locate where is the fault. Therefore, we need to use special techniques and tools. And as I said, like it's called Megger, a device called Megger, to identify the location of the faults in underground cables. And it requires also expertise as well. Regarding the duration of outage, the duration of outage in overhead and underground systems is very large. It can be 14 to 48 hours to let the underground system back in service, while in overhead systems, it can be between 4 to 10 hours. So when we look about the duration outage, the overhead system is better, while in full faults, I would say like faults problem or fault occurrence, the underground system is better. Surge effect, underground systems, surge effect is smoothing down energy by absorbing by the sheath. The other thing, interference to communication circuits. Underground systems, there is no interference with communication circuits, while in underground cables sometimes, or in overhead systems, there can be some interference in communication, especially when they are overhead. The temperature overheats. The temperature overheats that can lead to the breakdown. It can be very common in underground cables. That's something something undesired, and that will impact the insulation material. Heats, very large heat will impact the insulation material, which will cause a permanent damage for underground cables. Those are the underground cables. This is how they look like. So we have single phase, three phase, and we have underground cables are associated with communication and associated with power, like the fiber optics cables. So this is part of single phase. This is three phase. This is another single phase but larger thickness. This is also single phase. Then we can look at it. There is a jacket, there is insulation material, there is another jacket, there is a sheath, then there is the outer jackets. So the outer jacket for protection, there is a sheath here. This is, can be used, it's connected to the ground. We will talk about it later, but it's the good thing about it. If there is a fault going on, then it will be line to ground faults. So we want the fault to happen inside the cable. We don't want that fault, if there is some fault going on or something wrong, we don't want that fault to go out for the people, because this underground cables will be under or very close to the people, the customers, or the people, not the customers, I would say like the people there. So if there is some faults going on, we don't want that fault to go to the surface of the earth or the surface of the ground. This will be electrocuted and dangerous to the people who are living in the cities. So we want the fault to be only happening inside the cable. Then we send the maintenance to fix the cable. We don't want to make a severe damage or kill or be hazards for the people. Okay, this is again how it looks like. This is a single phase power cable. Then when you look at it, start from inner to be the outer. Then you will see here, this is a conductor, or this is the, I would say like the wire, the conduct to conduct electricity, conductor. This is insulation material. Then this is sheath, we call it, it's a metallic sheath, and this is the outer jacket. So the sheath here, it's connected to the ground, and we are connecting this to the ground to make sure if there's a fault going on, assume there is some construction and they are making, they need to establish a new pipelines or whatever, they are, or then they are digging there. So if they are digging there, the machines or the compressor digging there, once they dig in there, they will damage the cable. When they are damaging the cable, there will be a line to ground faults. So a line to ground. So we want, when the damage happens, the currents move from here to here, from line to ground. We don't want the currents to be moving to the compressor, for example, and kill them, the people who are working there, the working team. So as a result, we are making this damage here, or we're making the short circuits happening there. Or sometimes some rats can go and start eating the cable. Sometimes can happen some rats because it's underground. When they start eating the cable, then when they reach the metallic sheath here, they will stop because their teeth cannot eat the metal, then they will stop. So this is another kind of protection for the rats. So we don't want them to start eat. They will eat the outer jackets, then they will reach the metal, then they will stop. So this is another safety. Okay. This is how the cross-section area of the single-phase underground cable. I believe this is one is used for very large value, around 400 kilovolts or 380 kilovolts. I believe this one is used in Aqaba cable, in Aqaba submarine. No, in Aqaba submarine, I believe it's different. No, in submarine there is an oil on it, so we will talk about it later. But this is common, 400 kilovolts. This is 110 kilovolts cable. And here is how they make, if they need to make the three-phase, this is how they're creating it. So the three-phase, all of them in one cable, this is a challenge. Construction of underground cables, we need to make sure the conductor provides the carrier to conduct the electricity. We have the insulation material, and to make sure it's insulation safe. And there is external protection for mechanical damages, chemical damages, electrochemical attacks. So therefore, when we look at it here, this is cable is used in low voltage power cables, which is between 50 to 1,000 kilovolts. So we can see that there are some areas like the first thing, which is called the conductor. This is a three-phase. Then the second thing we call them, um, where is it? I believe I labeled every material here. The insulation layer. Okay. Then the third things. Then number four, armor. Then the outer jackets. So again, this is conductor. This is bedding. This is insulation. This is outer jackets. And how about number four? I forget. Actually, it is armor or sheath. Sometimes we call it sheath. Armor. Then when you look at it here, um, let's talk in details. What does each one means and how can we use it? So conductor, this is used to transfer the electricity, as we know. Copper conductor is basically commonly used more than aluminum due to high conductivity. Aluminum is light and cheaper than the copper, but the density of aluminum is about 1/3 of the copper, which makes it the copper 3 times better than the aluminum. So therefore, it's required to have a large cross-section area when we are talking about the aluminum. Therefore, we sometimes it's very common to use copper in underground cables. While when we talk about the overhead transmission line, we said the overhead, the vast majority are aluminum, not copper. But in underground cables, you will see many underground cables, especially when we are talking about the low voltage level. Sometimes here or here, like a comparison between the copper and the aluminum, between the resistance, the diameters, the weight ratio. The aluminum is also lighter. The temperature rise, the other things. So here is like a table, summarize it. Again, we are talking about low voltage. Okay, just keep this in mind. Components of low voltage power cables. So in terms of the physical core structure, the core can be solid or stranded. So what do I mean by solid and stranded? Let's go back and see here. So those are stranded. We see strands, مشدود, and there is a solid. I'm not sure if we have a solid picture here. The solid, there is no strands at all. It's just like this. Just one wire and solid. In underground cables, we have these two. There is a solid and there is stranded. While in medium voltage and high voltage, all of them are stranded. There is no solid at all. Then the solid core for larger size of the conductor become too rigid to install and difficult to handle. On the other hand, the stranded will be easier. The strands can be 6 strands, 12 strands, etc. And the other thing, which is related to, we need to make sure the currents to make it can handle, we prefer to use, or to make it for the easy to handle the shape or handle the conductor size, we prefer to use the stranded. In the terms of the conductor shape, the core can be circular, third circular or quarter circular, which achieves a better space factor and reduces overall diameters of the cable. And the other thing, stranded conductor size range, which can be between 1.5 millimeters square to 400 millimeters square for a 2-core, 3-core, and 4-core cables, from 50 to 2,000 millimeters square. That was for 3 or 4-core cables, while for single 4-core cables, we can use 50 to 2,000 millimeters square. What do I mean by 3-core and 4-core cables? Here's an example for the cable. We can have phase A, B, C. This is a 3-core. Or we can have A, B, C, and a neutral. This is a 4-core. While this is 4-core. This is a 3-core. While when we talk about the single core, there's only one phase. This is a 1-core. Okay? The following about the resistivity, there is a silver, copper, thin, tight copper, aluminum, and nickel. So we can say that the nickel has higher resistivity than the copper and aluminum, then the aluminum, then copper, then silver. So we prefer again to use copper or thin copper, tined copper there. The other thing, the insulation layer. The insulation, it's very important to insulate the conductors between each other and the conductor from the metallic material or the overall things. So the main insulation material is used is PVC in low voltage. And again, we're talking about the low voltage. PVC is the most commonly used, and it's suitable insulation thickness of on the thickness depending on the voltage level, larger voltage level, larger thickness, and the bedding. The bedding is used to separate the armor from the insulation layer. It's just like a very thin layer made from PVC. It's very thin. It's just like a bedding to separate, just separate for separation. And the armor, again, armor, as I said, it's used for protection from if there is a fault going on, internal fault, or from the rats. It can, like, if there is a rat. It's also, in addition to all of those, also to prevent mechanical strain, mechanical stress. It's also going to provide to grounds. The outer jackets, of course, the outer jackets protect everything, interior cable from everything. Then it's also, we need to make sure this jacket should not absorb moisture. It should resist the chemical interactions, resist fires, resist corrosions. All of them, the outer jacket must handle all of this. How about medium voltage cables? Medium voltage cables is very similar, but we will see it's more complicated. Here in the past, it was 5 components. Now we have 8 components. Medium voltage, anything between 1 kilovolts to 66 kilovolts. Okay, so here is number 1, 2, 3, 4, 5, 6, 7, 8. So let's talk about it. Number 1, the conductor. As we said, the conductor must be stranded. Then number 2, the inner semiconductor materials. This layer consists of carbon powder coated with cloth tape, or consists of mixture of carbon, polypropylene, and casting directly to the conductor. This layer to help regulate the electric field on the inner surface of the insulation material. Why? Because in the past, when we're talking about the low voltage, the electric field was neglected, but here electric field really matters for us. Then we have the insulation layer. So here for electric field, here's conductor, here's the insulation. Inner insulation layer, we call it inner. So the inner insulation layer is made from materials called XLPE. Number 4, this is another call it outer layer. This consists of the same material as inner, the same material as inner, and it's used also to regulate the electric field as well for the inner. Then we have a metallic shield as well on number 6 or number 7. This is metallic shield. The metallic shield provides a protection for mechanical stress, protection from faults, protection from rats, etc. Then the other thing, there is a bedding. The bedding from the PVC for anti-moistures. Then the last one is the outer jacket. As we said, the outer jacket will produce, can cover everything from humidity, etc. Now, let's talk about the high voltage cable, then we will stop it today. So high voltage power cables, it can be used between 66 kilovolt to 375 kilovolts. Then there are several things. This is a single phase, by the way. There's number 1, 2, 3, 4, up to number 9, which is more complicated. Here's the cross-section area. You will see the thickness is very large. So there is a conductor, the inner semiconductor layer, the insulation layer, outer semiconductor layer, beddings, metallic shield, another metallic sheath, outer jacket, and anti-termite protection materials. So all of them were done. We can apply. Then here, let's talk submarine cables. Let's talk about submarine cables. Submarine cables, they are used in the connection between Jordan to Egypt. This is very common. So, and basically, we have them as a single phase. And I mean, not as, we have 4 submarine cables. That's what I mean. So there is one submarine cable, phase A, submarine cable, phase B, submarine cable, phase C, and a backup submarine cable. This is a backup. That's what we have. Then we will talk about it again next lecture. Any question? All right. That's it for today. See you inshallah in Sunday.
ان شاء الله يعطيك العافيه. بس سؤال اخير، هلا انت قلت